Good evening, everybody. Welcome to day one on week 13 of the semester. Today, we are going to continue talking about the topics of chapter 8, and hopefully we're going to finish them, and then we're going to move on to chapter 9. The last topic that we talked about before our exam review last week was the topic of how do I utilize solubility rules to predict the product in a double replacement reaction? So when it comes to this, understand that for a double replacement reaction, there are several steps that we must follow, okay? And let me just erase the work that we see here, and let me get started onto how did we come up with the answer? Give me a moment. Because I noticed that last week when we were doing this, students had a little bit of a difficulty. How do we even manage that? So the first problem that we have here, this compound is already a solid, so we won't be able to utilize the concept for double replacement reaction, but we could do the second and the third, okay? Let's focus on problems number 2 and number 3, okay? So conceptually, a double replacement reaction comes from the idea that we're going to have two ionic compounds. I'm going to designate them with the letters A, B, and C, and D. A is going to represent the cation of the first compound. B is going to represent the anion of the first compound. C is going to represent the cation of the first compound. D is representing the anion of the first compound. Put a 1 in the chat if so far makes sense. A and B is one ionic compound. C and D is another ionic compound. Great. Now, as a reminder, a double replacement reaction is going to be a reaction in which we switch of partners, okay? What does that mean? Well, the cation of the first compound is going to make a new group with the anion of the second compound. So that means that in the product, I'm going to have A plus now paired with D minus. So that's the exchange of partners. Now A is paired with D. Then, similarly, the cation of the second compound is going to be paired with the anion of the first. So that means that we're going to have a new ionic compound that is C plus B minus, okay? Put a 2 in the chat if the new pairs for the product make sense. Excellent. So the thing is that we're taking this to one step further. We're trying to utilize solubility rules we are going to determine which compound is aqueous, which means AQ, in other words, soluble in water, versus a compound that is insoluble in water, which means that we're going to label it solid. So the S is for solid / precipitate that is going to form in our reaction. We already observed in the example when I introduced this concept that here we have the combination, the double replacement reaction in which potassium iodide and lead-2 nitrate, when you combine them, we see that there's that yellow substance that is being formed. What is that yellow substance? Is the lead-2 iodide that is formed in the solution because lead-2 iodide is not soluble in water, okay? So going back to the example, and remember that your solubility rules are specifically right here on your notes, okay? And we explain them in detail, but we're going to utilize them to explain what's happening, okay? So at the end of the last lecture, I was mentioning to you guys, what about if I give you the reactants? Give me a moment. I might have been cut off because it looks like the internet was unstable. So let me just repeat my last statement. So in the last lecture, before our review, we were trying to understand that if I have two reactants, okay, so for example, in reaction number 2, I have calcium acetate and I have sodium carbonate. Both of those compounds are aqueous. Let me illustrate why each of them is soluble in water. According to the solubility rules, okay, rule number 3 specifically says that anything that is paired with nitrate or acetate, any cation, it is soluble in water. So because of rule number 3, it makes sense that calcium acetate is soluble in water, so that's why we label it aqueous. On the other hand, we have sodium carbonate. So when we look at the rules here, rule number 6 tells us, hey, carbonates tend to be insoluble in water unless you pair them with lithium, sodium, potassium, or ammonium. If you pair them with any of those 4 cations, then they become soluble. So that's why sodium carbonate is aqueous. Now, we have to remind ourselves of the work that we did in chapter 3 when we are predicting the products of this reaction, okay? So you guys need to remember that ionic compounds can be a metal and a non-metal. We can have polyatomic, we can have a metal and a polyatomic. So you must recall that information in order to do these problems. So if I look at my first compound, which is calcium acetate, I need to recognize that calcium acetate is composed of quote unquote A and B. Remember, A is my cation, B is my anion. So how do I know who's my cation and who's my anion? The first element is my cation. In this case, calcium. Calcium lives in group 2A. So that means that it has a charge of 2 positive. Acetate is a polyatomic ion. C2H3O2, and it has a charge of -1. Put a 3 in the chat if the breaking of the ions based on the chemical formula for calcium acetate make sense. If it doesn't make sense, make sure that you please review the charges that polyatomic ions have, and also type 1 metals and type 2 metals, okay? Calcium is a type 1 metal. Let's move on to the sodium carbonate, okay? So the sodium carbonate is going to represent C and D, quote unquote, where C is the cation, D is the anion. Sodium lives in group 1A of the periodic table, so it's going to have a charge of +1. Carbonate is a polyatomic ion, and it has an overall charge of -2. Put a 4 in the chat if the breaking of the ions for the second ionic compound makes sense. Okay, so the first product in this double replacement reaction will be when A pairs up with D-. What does that mean? When calcium pairs with CO3, 2-. So when my A+ and my D- come together, that means that I have Ca +2, CO3 -2. Okay? Then I have the other compound where C is paired with B-. What does that mean? Sodium +1 is paired with my acetate. Let me write that down. So I have Na+1, C2H3O2 -1. Okay? Put a 5 in the chat if the work to develop the compounds in the products makes sense. If it doesn't make sense, any question? I only see 2 people, 3 people. There's 11 of you guys. Okay, so far so good. So we need to write down the chemical formulas for that AD and CB, okay? So this is when, again, we have to recall all of that information that we learned in chapter 3. This is how we do it. We learned previously that when it comes to ionic compounds, basically the number before the charge becomes the subscript of the neighbor. But in both of these compounds, we can see that the charges cancel each other. So what is the overall chemical formula for A and D? CaCO3, because the +2 cancels with the -2. In the case of the sodium and acetate, the +1 in the sodium cancel with the -1 in the acetate. So the chemical formula for C and B is going to be Na C2H3O2. Okay, those are my chemical formulas. Now, taking into account CaCO3 and NaC2H3O2, I go to my solubility rules and determine if they are soluble or insoluble in water. So I'm just going to write them, as you can see, right there in the corner. Let me explain these observations that we had here. So I have calcium carbonate as a compound that I'm trying to investigate. And then I have sodium acetate as the other compound that I'm trying to investigate, okay? So when I look at calcium carbonate, I have to look at where carbonate is in my solubility rules. Carbonate is part of the crew for for number 6, right here. The rules for number 6 establish that if I have a compound with carbonate, sulfide, phosphate, or hydroxide, if they are paired with cations, they form solids unless those cations are in rules 1 and 2, which means that those cations are lithium, sodium, potassium, and ammonia. Okay, so in this case, because CO3 is paired with calcium, this is insoluble in water, so we label it S. So if we were going to do this reaction, we are going to form a solid, and that solid is going to be calcium carbonate. What's going to happen to the other compound that we form, which is NaC2H3O2? Well, we can see that rule number 3 tells us that if you have acetate, C2H3O2, anything you pair with them will be always soluble in water, so we label it aqueous. So that sodium acetate is going to be aqueous. So in this reaction, when we have to predict who's going to form the precipitate that will be observed in the reaction, for this reaction, our answer will be calcium carbonate. Put a 1 in the chat if you want to do one more example to just solidify this concept. Great. Let's look at the following example. We have silver nitrate and we have potassium phosphate, okay? So remember, first ionic compound is going to be A and B. Second ionic compound is going to be C and D. These two ionic compounds have a metal paired with a polyatomic ion. So when I break that AgNO3 into ions, it's Hg plus 1 and NO3 negative 1. Because the charge of NO3 is always -1, and silver is one of those type 2 metals that only has 1 charge. Then the second compound that I have, K3PO4, my cation, meaning the letter C, is going to be potassium. Potassium lives in group 1A, so it's going to have a charge of +1. PO4 is a polyatomic ion that has a charge of -3, okay? Now we're going to switch up the partners. Hg is going to make a compound with PO4 -3. So I ask you guys, what is the chemical formula when we have Hg plus 1 and PO4 -3 coming together to make a compound? Let's write it in the chat. Great job to you guys. For the people that answer Hg3PO4. Because remember, we learned this in chapter 3. This number is going to be the subscript of the phosphate. This 3 is going to be the subscript of the silver. So that's why it's Hg3PO4. Let's write the correct chemical formula for the second compound, which is made out of K plus and NO3 minus 1. So when I have K plus and NO3 minus 1, great job, you guys in the chat. Exactly. The chemical formula is KNO3. Okay. So now I have to compare what's going to happen in this reaction when I have these compounds forming in the double replacement reaction. Well, understand that we go back to our solubility rules. Remember that we have Ag3PO4 and we have KNO3. Let me zoom into the solubility rules. Let's start with KNO3. Is KNO3 soluble in water or insoluble in water? Great job, you guys. Exactly. It's soluble in water. Why? Because when we look at it, rule number 3 tells us anything with nitrate is soluble in water. So that means that this is going to get a symbol of AQ, aqueous, because it can mix with water. Remember that S, usually that's the mistake that I see students make. They are like, oh, S, that means soluble. No, S means solid, meaning that that compound will precipitate, okay? So if it's soluble in water, we're going to label it AQ. If it's insoluble in water, we're going to label it S because it forms a solid. So when we look at Ag3PO4, is that soluble or insoluble in water? What about Ag3PO4? Dominique, I like your answer. Which rule? Great job, Maria. Which rule tells us that Hg3PO4 forms a solid? Excellent job, you guys. Rule number 6. Because rule number 6 tells you, hey, carbonates, which you can see it highlighted in yellow, sulfides, phosphates, and hydroxides. Those 4 are insoluble in water unless they're paired with sodium, lithium, potassium, or ammonium. It is not paired with any of the cations on 1 and 2. So that means that in our reaction, this is what's going to form the solid, the silver phosphate. So here, we label this solid, we label this aqueous. Questions. When we have a double replacement reaction, can we predict which of the products is the one that is going to form a solid, aka a precipitate? Great. Since there are no questions, let's move on to the next topic in chapter 8, which is solubility. Solubility is defined as the maximum amount of solute that dissolve in a specific amount of solvent. Solubility depends on two things. It depends on temperature, and it depends on pressure. Now, these two parameters that can affect solubility actually are influenced by the state of matter of the solute in the solution. As you can see in the first group of the bullet points that are underneath that depends on temperature, you can see that it says most solids, okay, as you increase the temperature, you increase their solubility. And if we look closely at the graph that we have on the right side of the slide, we can actually see illustrated. Here, you can see in the x-axis how temperature is present. In the y-axis, this is representing the solubility, specifically of a solid, okay? Overall, in 100 grams of water as we increase the temperature. And you can see that the majority of these solids, as you increase the temperature, they are more soluble, okay? Now, understand that if we have gases, for gases, the trend is that the solubility of gases is going to specifically decrease if the temperature increases in that solution, okay? Now, one example for this is actually how fast soda can become flat if you leave it at room temperature, okay? Or I don't know if this has happened to any of you guys, or if you know anybody that this has happened to. So maybe you guys have heard of this. People leaving their sodas inside of the car on a hot day. I think the worst case that I've seen was at the Vallarta supermarket in Escondido in the summer, where, you know, Escondido can get pretty hot. Now, on a hot summer day in Escondido, when it's like, let's say that day was like 110, I want to say. Now, there was a spectacle in the parking lot of just sodas exploding inside of a car. Just those 2-liter jugs were just exploding because it was so hot outside and it was so hot inside of the car that the gases that were inside of the carbonated drinks basically lost their solubility, accumulated, and because the container, basically the 2-liter jugs, cannot, contain all that gas that is maintained, you will see, it was just so sad, that the sodas were exploding. Thank you, Katie. Exactly. There was a sticky mess. I was just like, poor, I didn't record it, but I was like, oh, that is so sad. I imagine that person had to pay for a car wash, get their car detailed, because there's nothing you can do. The gases that were in the liquid, okay, became less soluble. They started accumulating, and they are not just going to be contained. They're just going to leave. So that's why you will see the caps just, just flying around, and then you see the gushing of the soda. It was just one of those things that I was like, wow, look, this is a teachable moment. But then I was like, this is unfortunate. I don't want to be in somebody's business car And then all of a sudden they're like, what are you doing? I'm like, recording this for my class. Anyways, but I just wanted to illustrate. So be careful, you guys. If you have a soda and it's a hot summer day, please don't leave it in your car, because you may be involved in a sticky situation, literally, just because the gases that are in the liquid in the soda are going to become less soluble, accumulate, and it could pop, okay? Now, another thing, there's a question in the chat. Does this relate to how sodas explode when they are shaken? Yes, because at that point, it is very similar. When you shake the soda, because we're talking about the next parameter that affects solubility, pressure. So whenever sodas are created, you can see that it was because the gases in the soda were pressurized into the liquid. And all of this is given by Henry's law. Now, when you shake the soda, what happens is that those gas molecules that were in the liquid try to escape. And then when they accumulate, even if you touch a soda after it's been shaken, which I don't know if people have done it, but I for sure have done it to my siblings. I have two brothers, one older, one younger, just to play pranks on each other. We used to do that. We'll shake the soda and be like, here, I brought you your drink, just to see the soda go everywhere. It happens, right? Like, I don't know. I was like that as a sibling. It's innocent fun. Until your mom is running behind you with the chancleta around because you're not behaving. But aside from that, so at that point, when you shake the soda, basically the gases that have been pressurized in the liquid are trying to escape. So that's why even when you open it, you hear the gases trying to escape. That's when you hear the psst moment when you open the soda. But the thing is, like, if all of them are rushing really fast, then that's when, you know, the soda is escaping all over the place. But all of that is given because, again, when it comes to gases as a solute, and then you're trying to put them in a liquid, it is known that higher pressure is going to allow more gas molecules to dissolve in the liquid. And then in addition to that, if you cool the solution, remember that gases are going to be more soluble when they are at lower temperatures. This is another reason why, for example, I noticed that sometimes people buy cold drinks and then they leave them to get to room temperature, and all of a sudden they're like, why did my soda get flat so fast? Well, because at colder temperatures, the gases remained in the liquid, but if now it's at room temperature, then the gases start escaping the liquid. And the minute that you open that soda, they're just going all over the place. And the more gas molecules escape from your carbonated drink, the flatter is going to become over time, okay? But as you can see, all of that is given by Henry's law. So now that we have talked about solubility, let's move on to section 8.3, which is where we actually look at chemical equations for solutions formation. So when it comes to this, we are specifically going to talk about electrolytes, okay? So what are electrolytes? Electrolytes play an important role in the body because they are necessary in order for the body to have proper function, okay? So commonly, when you look at electrolytes, like for example, if you consume products like Smart Water is said to have electrolytes, okay? And understand that these electrolytes, as you can see, they balance the fluids in your body, they maintain your blood's proper pH. pH is something that we're going to talk about in chapter 9. And very importantly, because you need these ions, and you can see you can have sodium, you can have potassium, you can have chloride ion. They carry electrical signals to power the nerves and muscles. And many communication systems, specifically in nerves and muscles, are carried out by ions. Now, what makes a particular electrolyte? Because we have different types of electrolytes. As you guys can see, we have three main different types of electrolytes. We can have strong electrolytes, we can have weak electrolytes, and we can have non-electrolytes, okay? Let's look at the difference between the three. Starting with a strong electrolyte. So in a strong electrolyte, it's going to be specifically a solution in which your solute completely breaks into ions. That's what makes a strong electrolyte. So for example, if you happen to be sick at home, and then all of a sudden you need Gatorade to just keep yourself hydrated, because one of the things that happens, like specifically if, let's say that you have a stomach flu and then you have been purging or vomiting, okay, as part of the process of your sickness, then one of the things is that you're getting dehydrated and you need to replenish with electrolytes. You don't have to run to the store and get Powerade, Gatorade, Smart Water, whatever. You can actually make the electrolyte at home. Basically, if you call the nurse helpline, they can give you the recipe of how to create an electrolyte drink. Usually they say dilute your orange juice and add some salt. Why the salt? Because salt is going to be the solute that when you put it in water, as you can see here for sodium chloride, it completely breaks into ions, okay? Now, it is known that if you have something or a solution that is a strong electrolyte and you try to pass a current through it, you can even pass a current through it, and the light bulb is going to symbolize that these ions are present specifically in the solution. Because you can see here that in the different poles that we have for the light bulb, the ions are going to be attracted to them, and that's how the current is going to be passing through in order to light that light bulb. Now, we can also have what is called a weak electrolyte. And what makes a weak electrolyte is going to be a solution in which the solute that you put in it is going to have some ions, but it's going to be mostly molecules. Here we have the example of hydrogen monofluoride. If you put hydrogen monofluoride in water, you can see that there are some HF molecules around. And you can see that the majority of them are HF molecules. And occasionally you're going to see the ions by themselves. That is what's considered a weak electrolyte. In addition, if you actually try to pass a current through a weak electrolyte, as you can see, our light is going to be dim simply by the fact that now that since we don't have that many ions around, then that electrical current cannot pass through efficiently. Lastly, we have non-electrolytes. And by definition, a non-electrolyte is going to be an aqueous solution in which your solute does not break into ions at all, okay? So the molecules dissolve, but it doesn't break into ions. So here we have the example of table sugar. In other words, sucrose just being placed in water. So if you have sucrose in water, understand that this is a non-electrolyte. because it doesn't form ions in the solution. In addition, if we try to actually pass a current through a non-electrolyte, you can see that your light bulb will not even turn because the solute does not break into ions. Any questions about the definitions of the different types of electrolytes? Great. Now let's take a moment and go through many of the definitions that we have taught so far in chapter 8. So I'm going to give you guys 3 minutes to pair the terms that we have on the left side with the definitions that we have on the right side. Okay, let's match the terms with the different definitions. Let's get started with number 1. What is the definition of solution? Let's put it in the chat. What is a solution? Great job. Letter F. What is the definition for solute? Solute. Great. Letter C. What about solvent? Great. Letter G. What about the term soluble? Great. This is letter A. What about alloy? Awesome. You guys got this. What about aqueous? Good job. And lastly, strong electrolyte. Great. So these are the definitions for the terms that we have discussed so far. Now we are going to dive into the math portion of chapter 8, which is when we talk about solutions, how do we express the concentration that we have in a solution? Now you can see that when it comes to the concentration of a solution, we can express it in different ways. We can express it as mass percent. We can express it as volume percent. We can express it as mass per volume percent, and lastly, molarity. So even though these are all different, okay, the one that I want to focus on specifically is going to be molarity, because the molarity is the one that is mostly used when it comes to chemistry and other disciplines in science. Now, mass percent, mass per volume percent may be utilized. And understand that here you're just comparing the mass of the solute divided by either mass or volume of the solution times 100%. That's where it comes. But when it comes to the math, you guys, molarity is the only one that I'm going to hold you guys responsible for. So let's just discuss more in detail. What is molarity? So molarity is defined as the moles of the solute that I have in a solution divided by the liters of the solution. So every time we talk about molarity, it's always in units of moles per liters. Always, always, always. Okay. So, for example, if you have to make a 1 molar solution, okay, of sodium chloride, understand that in essence, what you're doing is measuring out 1 mole of sodium chloride, and then you're filling up the volume. So as you can see, the solid is going in. But when it comes to the volume, what it really means is not that you're going to dump 1 liter of water in it. No, you're going to add enough water until you reach the 1 liter mark. Okay? So that's what it really means. So let's actually do some practice problems on molarity so we can understand what is required of you guys when it comes to assignments and examinations. Here we have the first problem. It's asking, what is the molarity of a 0.500 liters NaOH solution if it contains 6.00 grams of NaOH? Okay? So take this into consideration. As I just mentioned, when it comes to molarity, we need to keep in mind that molarity equals moles of solute. In this case, your solute is going to be NaOH. Then we're going to divide it by the liters of the solution. We can see that in this problem, we already have the volume for the liters of solutions that we need. But when it comes to the moles, we don't have here a unit of moles. We have grams. Now, previously, earlier in this semester, we learned how to convert from grams to moles. So in this question, okay, in order to get the moles of solute, we have to say, well, if I know I'm given 6.00 grams of NaOH, and I need to convert it to moles of NaOH. What's going to be my conversion factor? How do I convert grams to moles? What is my conversion factor? Let's put it in the chat. No, not Avogadro's number. I agree with you, Kiyomi. Yes, molar mass. Okay. And then how do we get molar mass? Remember that the molar mass is obtained specifically from the atomic mass for the elements at the periodic table. Okay. So since we need molar mass, then we need to calculate it. So if I have sodium hydroxide, to calculate its molar mass, what I have to tell myself is, well, in this compound, I have sodium, I have oxygen, I have hydrogen, and I have one of each. Then I'm going to take the one sodium, the one oxygen, and the one hydrogen, and I'm going to multiply times its molar mass. I'm going to utilize the molar masses that are in the front of the textbook. So sodium is 22.99 grams per mole. Oxygen is 16.00 grams per mole. And hydrogen is specifically 1.008 grams per mole. Here I'm multiplying by 1. So all I have to do is add $22.99 plus 16 plus 1.008. And the molar mass of NaOH is going to be 39.998. Now that I have that, I can convert to moles. All I have to do is say 6.00 grams of NaOH. I'm going to divide by 39.998 grams of NaOH in 1 mole of NaOH. Once I have done that, the grams of NaOH cancel each other. And when I do 6.00 divided by 39.998, I notice that if I round it to a correct number of suffix, which is 3, this is equivalent to 0.150 moles of NaOH. And now that I have the moles, then I can plug it into my equation. Which says that, okay, moles of solute is 0.150 moles divided by the by the volume of the solution, 0.500 liters. My calculator display shows 0.3. But because of sig figs, I need to actually put 2 zeros after the 3. The unit for molarity is a capital M. So the final answer for this problem is 0.300 molar. Okay? Let's do a practice problem when it comes to this. Here we have two typical practice problems when it comes to molarity, okay? So let's start by doing number 2. And then I will go over number 1. So in number 2, it says, if 0.885 moles of copper 2 sulfate are dissolved in enough water to make a 0.7 or 0.070 liter solution, what is the molarity? Okay, so in question number 2, I say molarity equals moles per liter. So in this question, you need to identify that your solute, which is copper 2 sulfate, is already given to you in moles. So all you have to do is 0.885 moles of copper 2 sulfate. We're going to divide it by 0.070 liters. So for those of you that have a calculator at home, what result do you get? Let's put it in the chat. Great. 12.6, because that's the correct answer, rounded with the correct number of sig figs, which is 3. Or actually, the correct number of sig figs will be 2. Let me fix that. Right? It'll be 12 molar. The reason is because this has 2 sig figs. This has 3 sig figs. So if we round it to the correct number of sig figs, it's actually 13 molar. Put a 1 in the chat if it makes sense. Why 13? Good. Let's go over problem number 1, which is asking you to determine the grams of solute that you need to prepare a particular solution. This is something that is one of the main calculations that you do when you work in the laboratory. Like, how many grams do I need of solute to make this concentration for a particular solution? Let's go through the problem. The problem number 1 says, how many grams of ammonium carbonate are needed to prepare a 0.5 liter of a 0.50 molar ammonium carbonate solution? Okay, so for here, we need to identify, well, I know that molarity equals moles of solute divided by the liters of the solution. I have been given the molarity of the solution and I have been given the volume that I need for the solution. But what I need to find is grams. Out of this, the only thing that can take me to grams is moles. So the first step in a problem like this, you guys, is that you're going to isolate the moles term. So when I rearrange my equation, I can say, well, moles of solute is going to equal molarity multiplied by the liters of the solution. So that's where we get started. We say, well, my molarity is 0.50 molar. My volume is going to be 0.5 liters, okay? Now, for those of you that are like, but how does the units cancel? Remember that the capital M is another way to say moles per liter. So that's how the liters cancel. And when I multiply these two numbers, the unit that comes out is moles. So 0.5 times 0.5 equals 0.25. So I'm not going to round yet. I'm going to use the numbers that I get. Now that I know how many moles of solute I need to change from moles of solute to grams. And in the first example that I gave you guys, I showed you how to go from moles to grams. What is the conversion factor that we need to change things between moles and grams? Great job, molar mass. Now, as you can see here, we have ammonium carbonate. Can anybody just take a guess? What is the chemical formula of ammonium carbonate? Chemical formula for ammonium carbonate. You can look it up online if you want to. Chemical formula for ammonium carbonate. Great. Thank you, Katie. NH4, 2 CO3. Okay. Now, because I need to go from moles to grams, I need to find the molar mass of this. So if I'm about to calculate it by hand, I'm going to say, well, this has nitrogen, hydrogen, carbon, and oxygen. So in this chemical formula, I have 2 nitrogens, 8 hydrogens, 1 carbon, 3 oxygens. Remember from previously, when we had learned about molar mass, if you have something in parentheses, the subscript that is outside the parentheses get distributed to everything inside, okay? So to calculate the molar mass of ammonium carbonate, we're going to do nitrogen times 2, which is 14.01 times 2. For hydrogen, it's going to be 8 times 1.008. For carbon, is going to be 1 times 12.01. And for oxygen, is going to be 3 times 16.00. So the results that we get from all those multiplications, we're going to add them. 14.01 times 2, that is 28.02, 1.008 times 8, that is 8.064. The carbon is 12.01. The oxygen is going to be 48.00. So we add all those numbers. Plus 28.02 plus 8.064 plus 12.01 plus 48.00. So what is the molar mass of ammonium carbonate? You can round it to 2 decimal places. What is the molar mass? two decimal places, not two whole numbers, but that's close. It's 96.09 grams per mole. So now that we have the molar mass, we can say, well, I know the moles that I have, 0.25 moles of the solute. In 1 mole of the solute, there are 96.09 grams of the solute. So when we take that 96.09 and multiply it by 0.25, okay? What do you guys get as a calculator display? Great, that's what I also got. Thank you guys. 24.0225. Now, this is the question. Let's go back to our original measurements given. This has 1 sig fig. This has 2 sig figs. So how do I turn the value 24.0225 into 1 sig fig? What would be the final answer? Excellent job, you guys. 20 grams. So my final answer here will be, I take 20 grams of my solute, I put it in a, in a container, I dilute it up to 0.5 liters, and that's going to give me my 0.5 molar solution of ammonium carbonate. Any questions on molarity, how to calculate molarity, how to determine the grams of solute that are needed for a solution? Any questions? Great. Since there are no questions, this is all for today.